The race toward AGI is driven mainly by large language models, and most of them are built on the transformer architecture. But what if the road to AGI doesn't go through transformers at all? In this video, we'll explain a new model architecture called Hierarchical Reasoning Model, or HRM, introduced in a recent paper of the same name. With just 27 million parameters, a fraction of the size of today's top reasoning models, and trained on only 1,000 examples, it managed to outperform top LLMs on some of the hardest reasoning benchmarks. Let's start to learn what it is about. Current transformer-based LLMs rely on chain of thought for reasoning. Given an input prompt, the model generates tokens that represent its reasoning process, which are fed back into the model and repeated until it produces a final answer. This kind of reasoning is external to the model. This forces the model to reason in human language. However, language is a tool for human communication, and human reasoning is not always expressed with words. Additionally, generating long chain of thought traces also comes with a cost. Many forward passes with a growing context window make the process slow and expensive. Instead, hierarchical reasoning models take a different approach, which is latent reasoning. Given a prompt, the model performs its entire reasoning process internally in a single forward pass and outputs only the final answer without the reasoning traces. While this concept might sound familiar from recurrent neural networks, we'll soon see it's far from a standard RNN. Inspired by the human brain, hierarchical reasoning models incorporate two recurrent modules. One is called the H module, which stands for high-level module and is used for high-level abstract reasoning and planning. The other is called the L module, which stands for low-level module, used for fast detailed computations. Both modules are coupled and working together as part of the reasoning process. We'll break down exactly how it works, but first, let's look at the results. Here are some examples from the benchmarks used to evaluate the hierarchical reasoning model. On the left is an ArcAGI example, an IQ test-like puzzle where the model needs to figure out rules from a few examples to solve the puzzle correctly. In the middle is Sudoku Extreme, a dataset the researchers extracted from existing Sudoku datasets and made it significantly harder to solve. On the right, we have maze-solving problems where the model must find the optimal path between 2 points. Now let's take a look at the following comparison table. Trained on only 1,000 training examples and with just 27 million parameters, the hierarchical reasoning model outperforms top reasoning models like DeepSeek R1, Claude 3.7, and O3 Mini High across these benchmarks. With that potential in mind, we are now ready to break down how this model works. But before we dive deeper into the paper, I'm excited to introduce this video sponsor, Emergent. Emergent is the world's first agentic vibe coding platform. Emergent lets anyone build and launch full-stack apps just by describing what they want. It's like ChatGPT, but for real, working products handling the front-end, back-end, logic, and database automatically. No coding required. I tested it by asking Emergent to build a modern archive, a site to display AI papers grouped by area, like natural language processing and computer vision, along with paper stats. In just minutes, it created a beautiful, functional site that pulled live data from archive and displayed the stats I wanted. Then I asked it to add LLM integration to detect trending research topics, and just a couple of minutes later, Emergent added that too. Here's the final result, fetching live data from archive, highlighting trending topics with AI, and presenting papers in a clean, modern layout. If you want to see how your own ideas could come to life, follow the link in the description to check out Emergent. Thanks to Emergent for sponsoring this video. Now, let's get back to the paper. Let's dive into the architecture of the hierarchical reasoning model. We'll use the following figure from the paper as our guide. First, the input goes through a trainable embedding layer, which turns it into a representation the model can work with. The hierarchical reasoning model then uses two coupled recurrent modules, working together at different timescales. The high-level module is the planner. It handles abstract reasoning and sets the overall direction. The low-level module is the doer. It runs fast, detailed computations to follow the high-level plan and work out the specifics. While this analogy may not be 100% accurate, it helps to understand the idea of the model. Note that we have a single set of weights for the high-level module and a single set of weights for the low-level modules. They are just drawn multiple times since they run multiple times in a single forward pass. The low-level module starts first. As input, it takes the input embeddings and the initial hidden states of both the high-level module and the low-level module. It then updates its hidden state. It then runs several recurrent steps, On each one, it consumes its hidden state from the previous step, together with the original input embeddings and the hidden state of the high-level module, which is still the initial one since the high-level module did not run yet. The low-level module runs for t steps. Once done, its hidden state is sent up to the high-level module. The high-level module processes it along with its own previous hidden state, updates its plan, and sends a new high-level hidden state back down. The low-level module then runs another t steps, now with the new hidden state of the high-level module, and sends the result back up. In this drawing we have 2 cycles, but this nested loop can continue for n cycles until the model converges. Finally, the last high-level hidden state is fed into a trainable output layer that produces the final tokens. To simplify a bit, the low-level module takes several quick steps to reach a partial solution. That result is sent up to the high-level module, which then updates its plan. The low-level module resets, takes another run, and the cycle repeats until the model converges on a final answer. Recurrent networks often suffer from early convergence, meaning that they finish after only a few steps. This interaction between the 2 modules in hierarchical reasoning model helps to overcome this and to achieve significant computational depth. When the low-level module starts to converge, the update from the high-level model acts like a reset for its convergence. This allows HRM to reach greater computational depth comparing to standard recurrent networks. Training hierarchical reasoning models is also different from training standard recurrent models. Normally, recurrent models are trained using backpropagation through time, or BPTT. In backpropagation through time, the loss is backpropagated through every single step, which requires huge memory and often becomes unstable when the reasoning chain is long. HRM avoids this problem by using a one-step gradient approximation. Instead of backpropagating through all t steps of the low-level module and all n cycles of the high-level loop, it only updates parameters based on the current step's computation, colored with blue in this drawing. This has 2 big benefits. One is that no matter how many reasoning steps we have, memory stays the same. Second is training stability, since it avoids exploding or vanishing gradients from long backpropagation chains. Based on what we've seen so far, there's something that is still unclear. We are talking about a significant computational depth, but if we only have n cycles, isn't the depth fixed? One more missing piece here is adaptive halting. After n cycles are completed, the last hidden state of the high-level module is not just passed to the output layer as drawn here. Instead, it first passes via a halting head that decides whether the model should stop or reason for another n cycles. This way, the model can dynamically adjust its thinking time depending on task complexity. For harder problems, it can continue reasoning for more cycles, while for easier ones, it stops early to save compute. Training this mechanism is done with reinforcement learning, where the model gets rewarded if it halts at the right time and produces the correct answer. The researchers demonstrate the necessity of depth for complex reasoning with the following figure using challenging Sudoku problems. On the left, the chart compares transformer performance when increasing its size, once by scaling depth with additional layers and second by scaling width. This shows significant benefit for the increased depth. However, the transformer performance still saturates, failing to benefit from increased depth after a certain scale has reached. On the right, we see a comparison between transformer, recurrent transformer, and hierarchical reasoning model in blue, which achieves near-perfect accuracy, highlighting how its hierarchical structure unlocks the benefits of depth in a way standard models can't. If you found this content valuable, please subscribe and hit the like button to support the channel. We also send 1-minute read summaries by mail about the papers we review here. Thank you for watching and stay tuned for more reviews of AI papers.